Welcome to our Introduction to Math. The fundamentals of math are built on understanding numbers. So we're going to talk a little bit about the numbers from the ACT test perspective. Some of the things that I've seen on the tests that I've had that pop up usually in the first 30 math problems. So we're going to take a minute and just review all of this terminology. You probably haven't seen it in a number of years, so it's a good thing to review. So the first thing is numbers, all numbers. Doesn't matter what it is, this is the whole set of all numbers. The first real break point that we see is to separate real numbers from imaginary. Now this part is not going to really get much into imaginary, but the ACT does use imaginary numbers on the test, so it's a good thing that we know what they're talking about. So the first thing is an imaginary number is represented with I. And some higher forms of math it may be a lowercase j, but for what we do and what we've seen on the ACT, I represents the square root of -1. Now, if you remember what a square root is, that means when I take this number, I can multiply some number by itself and get the number inside of this square root. Well, there's nothing that I can multiply times itself and get a -1. What we look at in math is we say, okay, I squared is equal to -1. And we'll get a little bit more into imaginary numbers later. I'm just sort of giving you the definitions. I squared is equal to -1. Therefore, when I take the square root of both sides, I get I is equal to -1. Now, some of the things that the ACT expects you to know is that if I squared is equal to -1, I cubed would actually be I times I squared. Well, I squared is -1, so now we just get -1 times I is -I. Then we have I to the fourth. I to the fourth is equal to I squared times I squared. Since I squared is -1, we have -1 times -1, which equals +1, and then the cycle starts over. For instance, I to the fifth would simply be a +1 times I, and it would be I all over again. So this is all I really wanted to cover on imaginary numbers, to let you know a little bit about them. If you've covered them in school, you may not have covered that much on them. Well, the ACT doesn't test it that often, but it's good to have a quick review of imaginary numbers. Now we're going to break down into the others. Real numbers starts with all numbers from -infinity to +infinity, including 0. Now, some of the terms that we use with these numbers is we can start with integers and whole numbers. These are the counting numbers, 0, 1, 2, 3, 4, 5, or -1, 2, 3, -1, -2, -3, -4, -5. So these are our integers, or we would call them counting numbers as well, or whole numbers. Now we get to where it gets interesting, and this is the kind of thing the ACT tests the most often. It's going to be rational numbers. Rational numbers are numbers that can be expressed as a fraction. They can be expressed as a fraction, and we'll look at some examples in just a minute. Irrational numbers cannot be expressed as a fraction. Usually this is going to be square root of 2, square root of 3, square root of 5, square root of 6, square root of 7, square root of 8, and square root of 10, and so forth. You'll notice that I skipped the square root of 1 because the square root of 1 is 1. 1 is a rational number. I skipped the square root of 4 because the square root of 4 is 2, and 2 is a rational number. I also skipped the square root of 9 because it's 3, and 3 is a rational number. So the ACT has had a number of tests where they will have a question that deals with identifying and working with these numbers. Now we're going to take a minute and look at some examples of these and work through them. I mentioned we were going to look at some operations with these numbers. These are the kind of questions the ACT has put on the test, usually in the upper 20s to the upper 30s range of a difficulty level. So let's take a look at one of them. And one of them is the square root of 2 plus the square root of 3. And they're asking you the question, would this be rational or is this irrational? Now, What you notice is we're adding them. If I'm adding them, they're going to stay irrational. If I did this, you could do it on a calculator, but you're not going to get an exact number because there's no way to represent this or this as a fraction. It's going to stay irrational. If I did it with a square root of 5, or if I said that plus 2, any of those combinations, once it's irrational, it stays irrational. If I just had square root of 5 plus 2, square root of 5 plus 2, doesn't matter that 2's rational, that's irrational. So when I add an irrational to a rational, it stays irrational. When I add an irrational to an irrational, it stays irrational. Okay, so that covers addition. The same would hold for subtraction. Now what we're going to do is look at multiplication. This is where it gets a little different. If I take the square root of 2 times the square root of 3, what I'm actually doing is multiplying the numbers, and I get the square root of 6. Well, the square root of 6 is still irrational, so this one is irrational. Okay, but let's take a look at some that might actually work. If we do the square root of 2 times the square root of 8, both of these are irrational. But when I multiply them, I'm getting the square root of 16, which equals 4, which is rational. Let's take a look at the next one. Square root of 3 times square root of 27. Square root of 27 is irrational. The square root of 3 is irrational. But when I multiply them, I get the square root of 81, which is 9, is rational. So I want you to see how there's a difference when we add versus when we multiply. Now let's take a look at divide. If I did this one in divide, I would break this apart. And this would become the square root of 4 times the square root of 3 over the square root of 3. The square root of 3's would cancel. Square root of 4 is just 2. So the square root of 12 divided by the square root of 3 is rational, even though both of these are irrational. If I do another one, the square root of 48 over the square root of 6, let's see what happens with this one. Well, the square root of 48 would break into the square root of 16 times the square root of 3 over, now this is going to break into the square root of 2 times the square root of 3. Well, we're off to a pretty good start because our square root of 3's cancel. Now we have this. This becomes 4. So we just end up with 4 over the square root of 2. Now 4 over the square root of 2. Remember, we're going to try and get this radical out of the denominator. We'll multiply by the square root of 2 over the square root of 2, and we get 4 square roots of 2 over 2. These cancel and give me 2 square roots of 2, which is still irrational. So in some cases, when you're trying to work your way through these numbers, you need to go all the way through and break it down. But remember, when they're multiplied, we can break them apart like I did with this 12 here. I can break that into a square root of 4 and square root of 3. When I got to the 48, I can break it apart as well. All right, so these are some of the basic rules that help us understand rational and irrational numbers. Now we're going to take a minute and look at 3 properties of arithmetic that we really want to remember. You probably covered these in like the 5th or 6th, possibly the 7th grade, depending on which math track you're in. But we want to take a look at these. This is called the commutative, associative, and distributive properties. Okay, so first we're going to look at the commutative. And this is simply telling us that it doesn't matter which order we do something in, it still gets the same answer. So for example, if I said 3 plus 5, 3 plus 5 equals 5 plus 3. And then 3 times 5 is equal to 5 times 3. 3 times 5 is 15, 5 times 3 is 15. The name of that property is the commutative or commutative property. Okay? Now we get to associative property. This one says it doesn't matter how we group the numbers if the operation stays the same. So 2 plus 4 plus 6 is equal to 2 plus 4 plus 6. Now yes, we do what's in the parentheses first, but since we're adding, watch what happens. 4 plus 6 is 10, plus 2 is 12. 2 plus 4 is 6, I do that first, then I do the add 6 to it, and I get 12 as well. So this one stayed the same. Let's see how it works with multiplication. 2 times 4 times 6. Well, 2 times 4 is going to be 8. 8 times 6 is 48. That's exactly the same as if we said 2 times 4 times 6. Well, 4 times 6 is 24, times 2 is 48 as well. So these are our two properties here. Now the distributive property means that we're going to distribute the number in front through the parentheses. Okay, now with numbers it's a little easier because all we would do in numbers, if you're going to be doing this right, is you would say this is 7, 4 plus 3 is 7, times 5 is 35. But you can also break it apart like this, and we can say 5 times 3, which would be 15, plus 5 times 4 is 20 equals 35. So that works the same. We can do it this way. It doesn't matter whether we have the 5 in the front or the 5 at the end, it's going to get the same. This would give me 3 plus 4, which is going to be the same as the 3 times 5, and then the 4 times 5 again gives me my 15 plus 20 is equal to 35. Okay? I wanted you to have a review of these before we work through some math. The next video is going to cover PEMDAS, the order of operations. Then we're going to look at some problems that combine all of this, and we're going to let you work through some. Then we'll come back and review those. So let's go ahead and look now at the order of operations. Okay, PEMDAS, order of operations. Parentheses come first. You've learned that since the very basics of math. Always do what's in the parentheses first. Then we do the exponents. Then we do our multiplication, then division. Then we would do addition, and finally subtraction. P-E-M-D-A-S. PEMDAS. Now let's look at some examples between each layer to understand how they work together. If I had a problem that had parentheses and an exponent, how would we do this? To do this, we would add the 7 plus 11 because that's inside the parentheses. Yes, addition comes way down here, but finishing the parenthesis comes first. So now this one would become 11 to the third power. Then we would raise it to the third power and get our answer. Okay? If I'm looking at exponents versus multiplication, if I had 4 times 3 raised to the second power, what that tells us is there's nothing to really do in the parentheses, so the next thing is exponents. Square the 3 first and get 9, then multiply by the 4. It's a very common mistake that people will make is they will do it on their calculator and they will say 4 times 3. The calculator gives you 12, then squares it and you get 144. But you can see the answer should be 9 times 4, which is equal to 36. The ACT will have both answers on the test because they know people make these kinds of mistakes. Now if we looked at multiplication versus division, this is one that there are unique examples where it makes a difference. This one doesn't really matter. I'll show you as you look through this. But we keep in mind what the order is, and we always follow the order. It's a set of rules we don't change, and then when we run into that exotic example where it really makes a difference, we get it right. But if I had 4 times 3 over 2, I would say this is 12 over 2 is 6. Yes, I could go ahead and say 4 divided by 2. 2 goes into 2 one time, 2 goes into 4 2 times 3 is 6, and do it that way and get it right. But there are examples, now you may find them on the ACT test, where it doesn't work if you take a shortcut like that. Now if we compare a division versus addition, if I had 12 divided by 3 plus 2, I would finish the 12 divided by 3 first, get that answer, which is 4, add my 2 to it, and then I get 6 is the answer. I wouldn't say 12 plus 2 and get 14 divided by 3. That'd be wrong. Now between addition and subtraction, just like between multiplication and division, in most cases it doesn't matter because you saw earlier in the commutative property and associative property it didn't matter. Well, it doesn't matter a lot of the time, but there are times when it does. So what we'll do is if we had problem 2 minus 6 plus 3, that's going to be just like we saw before. That's going to be the same thing as if I had 2 plus 3 minus 6. In any case, I'm going to get a negative 1, and that's all there is to it. But there are unique examples where it will make a difference to have done the addition first before you do the subtraction, just like with multiplication and division. So I wanted to give you a quick run through on PEMDAS. Now it's time to work through some real examples. So if you'll look now, you should have in your handouts a series of examples we're going to work through, and we'll go back over those in just a few minutes. So go ahead and work those now, and then come back and watch the answers as we go through those. First, we look at the 15 divided by 3, and that equals 5. Then we look at the 12 divided by 4, which equals 3. So now we've done those two operations first. Now we focus on the plus, and combine them and get 5 plus 3 equals 8. And that makes 8 the answer. Now let's look at the next one. You see that you have the 14 minus the 6 in parentheses. Remember, that takes priority over everything. So now we're going to have a 2 times 14 minus 6 is 8. 8 and 6 is 14 over 4. Now we multiply. 2 times 8 is 16 over 4 equals 4. And that gives us the answer 4. Now the next one is one I put in so you could see it two different ways. Does it make a difference if I said 96 divided by 12 times 4 divided by 2? And you notice that the long bar is drawn here. And then I did the exact same problem, but I drew the long bar down here. Yes, let's see how it makes a difference. In the first one, we would say 12 times 4 is 48, divided by 2 is 24, and we would have 96 divided by 24, which equals 4. Now notice what happens in the next one. This is why order of operations is important. I would do the 96 divided by 12 times 4 is 96 divided by 48 is equal to 2. And 2 divided by 2 is equal to 1. Totally different answer, so make sure you watch these orders of operations. Now, remembering our parentheses, we go to this first set, and we're going to have a 5 outside. 12 plus 5 is 17, minus. Now we have 19 minus 14, which is 15, times 3. Okay, it's 5, not 15. Then we have 15, I was getting ahead of myself, is equal to 5 times 2, because this becomes a 2, is equal to 10, making 10 the correct answer for this one. So hopefully you got these right. Now we're going to continue on with another round of practice, and then we'll be ready to move on. For the first problem, we're going to be multiplying the 2 times each of the things inside the parenthesis. We don't really have a value here, so we can't solve it other than to do this. So we take the 4x times the 2, and that equals 8x. And then we take the 9y times the 2, and that equals 18y, and that's the answer. On the next one, we're going to do what's in the parentheses first, and there's nothing to do, but we're going to multiply the 5 times the 7, and we'll be getting a 35 from that. Then we're going to multiply the 5 times the 3y and get a plus 15y, and the 18y just moves over as it was, and we add it to it. So now we've got a 35, and then we got a 18y plus a 15y. So we combine like terms, and we end up with a 35 plus 33y. Now we're going to change things up a little bit, and we're going to start having a value for our variable. This one we start off with b is equal to 3. So we're going to substitute a 3 in for b in both places. And we're going to do what's in the parentheses first. So this gives me 30 times 3 plus 2 plus 2 times 3. Well, 3 plus 2 is 5. 5 times 30 is 150. Plus 2 times 3 is 6 is equal to 156. Now, on the next one, we know that a is equal to negative 2. The ACT loves negative numbers. So we want to make sure we get these right. We're going to plug in a negative 2 here, and we're going to plug in a negative 2 here. So 8 minus 2 is 6, so I end up with a 3 times 6 for the first part. That covers this. Now I'm going to have a plus 7 times 4 times negative 2 is negative 8. And a negative 8 to positive 6 gives me a negative 2. So now what I have is 3 times 6 is equal to 18, and 7 times negative 2 is equal to minus 14, and that gives me 4 as the answer. On our next one, we have 2 variables, and we have substitutions for both of those. So we're going to start with our x is negative 1. That gives me a negative 1 plus 3 inside this parenthesis times 3. Plus, now the next one's going to give me a 4 times 2 times negative 1 plus 3 times 3. That's what this is going to become. So now I do what's in the parentheses first. Negative 1 plus 3 is 2. So I have a 3 times 2 plus. So now I do this, and I get a negative 2 plus 3 times 3 is 9. And that's still in parentheses times the 4. So if I look at this, what I've got now is 2 times 3 plus. I take this and add it together. Negative 2 and 9 gives me negative 7, so I get 4 times positive 7. It was a positive 9, negative 2, my bad on that. Gives me a positive 7, and that gives us 6 plus 28 equals 34 for the answer to this one.